Welcome to our fifth lab. The purpose of this lab was to model any scenario we wanted. So I came across a video of a person accidentally hitting a bird with a golf ball, and I decided to model that. And the goal was to analyze the collision by recording the momentum before and after the collision, showing that momentum is conserved during the impact. For the models and fundamental physical properties, we used Python to simulate a collision between a golf ball and a bird, both represented as spheres. The simulation focuses specifically on their interaction during the collision and how their momentum changes. The main physics principles demonstrated here is the conservation of momentum, which means that the total momentum of the system stays the same before and after the collision. So that means the momentum of the ball and the bird before colliding equals momentum of the ball and the bird after the collision. For this experiment, the main physics concept is conservation of momentum. Momentum is defined as a product of an object's mass and velocity, and it is a vector quantity, meaning it has both magnitude and direction. And for a system of objects, the total momentum is the sum of the momenta of all the individual objects. The law of conservation of momentum states that if no external forces act on the system, the total momentum before an interaction, such as a collision, is equal to the momentum after the interaction. So the mass of every element times their velocity equals the mass of every element times their final velocity. So this principle applies in all directions, meaning momentum can be transformed between objects during a collision or interaction, but the total momentum of the system remains constant. And conservation of momentum is a fundamental concept in mechanics, and it allows us to predict the behavior of objects in collisions and other interactions, such as a bird and a golf ball. For the initial conditions of our model, we selected random values to secure a collision, and those were that the golf has an initial position of 0, 0.5, 0, velocity of 0, 8, and 0 meters per second, and it is stationary at 5 in x, 4 in y, and 0 meters per second with a velocity of 0, 0, 0 meters per second. And the ball has a mass of 0.045 kilograms, and the bird has a mass of 0.09 kilograms. Gravity acts downwards at 9.8 meters per second squared, and the simulation updates in a time step of 0.005 seconds. The system consists of the ball and the bird, while the surroundings include the earth, which exerts gravitational force with other external forces neglected. And for this experiment, the simulation updates the position and velocities of the golf ball and the bird in small time steps. In each step, gravity accelerates the objects downwards, changing their vertical velocity. The main loop also checks for a collision. When the ball and the bird gets close enough, it calculates their new velocities using the conservation of momentum for an elastic collision, as you can see in those lines of code. And this ensures that the total momentum before and after the collision is preserved. After updating velocities, the simulation moves the objects according to their current velocities. The program also calculates the momentum components in both x and y directions for each object and plots them over time. And the total system momentum is tracked by summing the momentum of the ball and the bird in each direction, showing that the momentum is conserved, especially in the horizontal direction when there is no external forces. Ground collisions are also handled separately by reversing and damping vertical velocities, but these do not affect the momentum exchanged between the ball and the bird during their collision. For our results, the momentum graphs show the x and the y components of momentum for both objects and for the total system. In the horizontal momentum graph, the collision is clearly visible between about 0.7 seconds, where the momentum of the ball and the bird suddenly change, and even during this moment of impact, the total horizontal momentum stays constant, showing that the momentum is conserved in the x direction where no external forces act. The values before and after the collision match, which confirms the conservation principle. In the vertical momentum graph, the total momentum does not stay constant because gravity acts downwards on the system. However, you can still see that the transfer of momentum between the ball and the bird during the collision, and overall, the graphs clearly show that momentum is conserved in directions without external forces, and they highlight how momentum is redistributed between the two objects during impact. The model worked as expected, showing momentum conservation during the collision. However, in reality, these results would differ. The simulation assumes a perfectly elastic collision, meaning no kinetic energy is lost, which never truly happens. We also ignore the mass distribution of the bird and any rotational effects it might have experienced. And additionally, energy dissipation through sound deformation or heat is not considered. The simplifications mean that while momentum is conserved in the simulation, in real-life collisions would involve energy losses and more complex motion. And in conclusion, the simulation successfully demonstrated the conservation of momentum during a collision. The graphs show how momentum is transferred between the ball and the bird, and while the total momentum of the system remains constant in the absence of external forces. Although the model simplifies reality by assuming a perfectly elastic collision and ignoring factors like mass distribution and energy loss, it does effectively illustrate the fundamental physics principle that momentum is conserved in isolated systems. Thank you.